We're happy to have you, Sergey Plesiev from Georgia State. I actually saw some of his work online about web-based GPU brain processing. I was very impressed by what I saw, and I thought, might be a good person to hear about another tool. Maybe not the people maybe are not as familiar as they should be, so it's an opportunity to learn about something new. So, Sergey, thanks for taking the time and take.
Yeah, thanks for inviting me. I'm always happy to talk about what we're up to here. And let's start with what we're up to here is like motivation, why to do what we're working on. So yeah, we're kind of living in the age of AI right now, right? Every like I don't know, anything I turn on talks about AI, AI risk, AI bliss, and all of the tools, and even person of the year is the CEOs of AI, and so that, but are we really getting there as community? Even though everyone is talking about AI, it's almost always just an LLM, right? And it's almost always one of the three big LLMs or something and something. So with AI, we get a lot of publications. It's a very compositional, it's very easy, relatively easy from technical standpoint. Maybe I'm simplifying, but put pieces together, you get a publication. So we have tons of publications that produce a lot of models. That's also good. And supposed to produce tools, right? Because the promise of AI and the excitement of AI is that we can easily use those tools. But yes, we have abundance of publications, but we don't have that many models available for use, and we practically don't have any tools to use. So according to the paper that I'm citing there that looked at the field of radiology, only 40% of radiology AI studies share their models, and deep learning models show the lowest availability, 11.5%. And importantly, those are just the models, which is practically a binary file from the perspective of a normal human who doesn't have years of engineering training, right? So if we'll look at model availability, like an interesting paper with this interesting statistics that in some subfield, like Australia shares all of their models, but I was wondering if maybe they don't publish that much, and maybe that's 5 papers that they publish all share the models, and that's but model sharing differs, and then when the model is shared, it's mostly shared like that. Yeah, you have a nice model, by the way, and then interactive shout out to the authors. But in order to use it, you have to be able to understand what's on the screen here. But even if you understand what's on the screen here and you're comfortable with the terminal, working in the terminal, then you have to have some years of suffering with Conda because Conda doesn't always work and Conda dependencies can easily get you in a loop. And probably you have non-technical friends who have tried this with LLMs because when LLMs came out, ChatGPT and others, I was telling my friends who used to ask me, "Hey, my Linux broke. What do I do?" and blah blah blah. Just ask ChatGPT because it helps me a lot, but it doesn't help a person if they don't know already what they're doing. So kind of the models are shared, but it's the green gray sharing. It's there, but only select people again can use it, not the people who mostly need to use it. So another problem with the current state, the motivation for what we do is yes, scaling laws, which just to remind you is when you get things, when you enlarge things in the deep learning models, whether it's depth, whether it's width, whether it's number of data on which you train, things become better. So, but scaling laws, yes, require lots of GPUs and mostly NVIDIA GPUs for those models. And larger models, yes, are always better, but there are plenty there are plenty of resources in the cloud, so let's scale and make bigger and bigger models. They will be better and better. Yeah, just larger clouds, larger data centers, and that's what a lot of people, a lot of big companies are now doing, building those larger clouds, larger data centers for larger and larger models. And even not a joke, we need nuclear reactors now near those data centers to power those data centers. Otherwise, they wouldn't get as big as we need them to be. But the problem with that is that even in the minds of scientific community, listening to all of that, this message kind of distorted and into the message that only the models that are as large as models that require nuclear reactor megawatts powering them are good, which is not true. And I'll show you. So another thing with all of those models, and I'm not privacy zealot or like I don't think everything is private and nothing can be shared. And I am using those online services and online models, but everything goes to the data centers. Yes, you have plausible privacy there. Maybe they will not be hacked. Maybe they will not sell your data to marketing company. You can hope for that, and like even the agreements and stuff. But when you're working with medical data, and when you're working with medical data on the spot, that might be a problem. So not all data can be transferred to the cloud. Imagine a patient just arrive and you want to, and the patient is not in a condition that they can give the consent for data going to the cloud, for example. There are ethical, legal reasons. There are protests with protection of trust of the users because, well, let's not go there. But there are other technical and administrative reasons. For example, yes, we can sign data usage agreements and start sharing data, but it usually takes months and months and months. I would have done the work by then already. Uh, yes. That's what I'm saying there. Another thing is sovereignty, right? When we are hooked to those big AI clouds, we are literally hooked to them, and only those models can work with that. We constantly need connection. But if we have our local models right here on our laptops, they are liberating in the following way. Those big models in the cloud are only economically feasible when they're working on bulk of data, doing batch processing. So when everybody needs to process or do the same thing, then they're very good. They're efficient in the speed of processing. So we're all chatting with the chatbot, a few billion people, fine. But if you're doing something unique or something one-off, this is an absolutely like an inefficient way to do. So sovereignty, when you have a model with you on your laptop, allows you to do unique things that you're interested in right now and only you're interested in. Another thing is we can have better and larger models in the cloud. We can sign data usage agreements and wait for another half a year or sometimes more, like several years, and get better results. But maybe this improvement that we're getting from large models is not worth the wait. The models that are small, that are here right now, that may be slightly wrong, can be much more beneficial because the result is not in perfection. The result is in actually what you need to get out of these models. And another thing that I will talk more closer to the end of my presentation about is even if the model is slightly wrong, but it's fast and it's giving you the output right now, and you can correct it and get corrected output immediately as well in the loop. locally again on your machine, that might be more valuable than waiting for the perfect model and then getting result tomorrow. So another problem with the big models and with the state of AI in our neuroimaging field right now is this disconnect between the way we share models and the way the actual users who we think will benefit from those models operate. For example, I had this story, my personal interaction with a radiologist who was manually labeling um, MRI images for a specific application. And I was training models on that. So I sent her a Nifty file with my labels, expecting her to be able to look at it. And basically, multiple interactions. And the story ended up that I made a movie with slices of the image slowly changing, put it on YouTube, and sent her YouTube link. So one reaction to that, especially if there are any programmers, engineers, machine learning ops people listening to me, maybe you're thinking in some condescending way of that person. But I've been in interdisciplinary field, I've been condescended upon from other side as well. And I don't think we should require everyone, professionals in their fields, to be able to use our tools and our tooling. The usage of AI models should be very easy and very simple for anyone, as simple as opening a browser and going to a web page or just point and click. So, uh, in that light, with motivation, our goal is AI models with top performance for regular users. So people who don't know about programming, never heard the word Conda, and yeah, but don't worry, we have stuff for developers as well, I will show. And we want minimal installation burden because we want these tools available behind firewalls, behind like the user who needs to run analysis of their private biomedical data that they cannot share should not be forced to work with their IT department or to do anything with their computer. It should really be point and click. And the models should be fast, personalized, and interactive. So by this, I mean that people should react, the models should react to my corrections, the way I'm making corrections, they interact with me, and I quickly get the result rather than running on the cloud in bulk. Cloud is good for bulk processing, and I will mention how our models can help there as well. But instead, when the model is personal, it should be interactive and should give you results. So the answer is brainchop.org that we created at least for the segmentation problem. And so this is a 1 minute video, and I don't know if you can hear the music. It has music, regardless.
I'll
I
tell
will
you,
just,
start and I'll tell you.
can you hear the sound?
No, are you sharing
No, maybe
sound?
there is a way for me.
Yeah,
Okay,
stop
well,
sharing and share optimized for video usually on Zoom works.
I think there are settings that where I can specify. Just one moment. Let's quick
Yeah,
if
take
we
your
can
time.
do.
Yeah. Yeah, or if you can stop and restart sharing on under share, you can choose to optimize for video. Or you can just pretend you can just talk
It
on.
doesn't. The voice is just the background. Doesn't matter. Let me shut up for a moment. We made Brainchop a few years ago with Mohammed Masood driving the work, and this video is like a 1 minute marketing video that Farfalla who created for it for the first version. Okay, so that was the first version where we used Papaya Viewer that is now is not maintained. And then Taylor Hanaik and Chris Rorden contacted us with their little tool Niview and helped immensely of turning Brainchop into, at least at the interface side, into what it is now today, and speeding up a lot of JavaScript things. And here's another 1 minute video about what we have right now, but I will demo it. This is just an overview of what it can do.
Sergey, as you're showing this, just to be clear for everybody, there's no server plugin here, right? This is running. Yes.
Excuse me, were you saying
Yeah.
that something?
So this is running in the browser, or is there a server plugin here?
Sorry.
Can you hear me?
Yes, the video has to play. Say it again.
So this is running in the browser completely, or is there a server here?
Everything. There is no server side. There is no
So
servers.
for those of you listening at home, your data doesn't leave your computer if it's running
Yes, there is no server side.
on the
It's
client.
everything. We bring computation to the data. The model comes to you, and I will show how it works. I will show like just a second. Yeah. No, I don't have the controls. I turn off the controls. Let's skip the video. So basically, oh wait. This is a good just example. We have tissue segmentation model, brains extraction models. I will demo it in a moment. Initial version, we had telemetry on, but now we went sort of crazy on the privacy. We do not collect anything. It's the moment you type in your browser brainchop.org, uh, whatever got to your side, it's only to your side, to your computer. Nothing goes back. Basically, that's bad. I would like to collect some vote because we do need stuff. So if you have a GitHub account and can give us a star, that's the only way for us right now to collect some statistics of how people using us. We may come back to this, but initially we were collecting the statistics, at least where people are coming from, and especially what we were interested in is how the models fail. And those are people who've tried it before we went to this current version. And let's do some demos. So this is an experimental version that I was rushing to prepare for this presentation. The actual Brainchop is right here. So you open it up, you have an example. If you have your MRI, you can just drag and drop. Nifty file, works file, MGZ will work, and many other formats. Uh, but drag and drop, and you have your file. You can quickly get, say, tissue segmentation, or even like when the quality is not the best. This is real time running on my laptop. This is the information about my laptop. Maybe I should go. It's Apple M2, and it is a laptop. Anyways, it's a powerful laptop. And inference time for tissue segmentation took half a second, right? Um, we can also, this is brainchop.org, something that you can try right now. But I'd rather demonstrate this to you, this version. and I'll explain later. So tissue segmentation is there, fine. So another powerful model that we have is skull stripping, basically, and it works on any modality. Let me do this. Oh, I didn't mention. You can save the segmentation, the result of the segmentation. Okay, what was it? Let's save it here. And then what happens? You can drag and drop and look at it again, or the segmentation with a shift can be overlaid on top. But since it's a brain, we don't see it's the same brain on top of the person, right? But if you have a segmentation, you can overlay images here. But let me first demonstrate the models. Another model that we have is this. It takes a little longer, but everything I'm demonstrating to you runs in real time. You can actually type this URL, neural.net brainchop.test, and run exactly what I'm running here. And then you have subcortical structures as well. And the good thing about this model is that let's take a strange MRI. So it's a little darker, etc. And if you run this light model that runs blindingly fast, you will not see any good result. It completely fails. But if you run this model, it will work and will get you subcortical regions and gray and white matter segmentation. But the model that does the same, but physically smaller, it has smaller number of parameters, so it runs faster. I will use it now because it runs in 2 seconds. And it gives you the segmentation of different regions. You can click on them, you can see what region is that, and the volume of that region, etc. Again, you can save segmentation and do other things. If you want, you can get segmentation, free-surface segmentation for 50 regions. But again, this is a difficult input. Let's see what it does. It fails completely on that input. And we have in the about, we describe our models and especially the icons that the models that have acts, they are very robust. They run on a lot of data. And we only have one model that runs very, very fast, Flash model, this with a zap sign. The models with a knife are precise, but only on good quality data that is like human connectome project pipeline processed. So if we run this 50 class model on the example file or any other better MRIs, it works quite well. You are getting, we can press C here and say see the segmentation, and again you can get the volumes, you can save the segmentation, etc. We even have the full free surfer Jessica Kiliano atlas here, so you're getting the complete free surfer atlas. But yes, it's the model. Oh, pressed too many times. Sorry. The model is fragile. It cracked the neck here, but the models that get subcortical and that get tissue segmentation are very robust. Let me show you the robustness of these models. So there's this mind-boggle data set. And to demonstrate how robust the models, I need to first show how the models are non-robust. So let's run this fast model.
Sergey has a question in the chat as you.
Yeah. I don't see it. If you can just read it.
So it says, where is the information regarding healthy versus disease condition? I'm not sure that that's relevant here.
The information is yours. It's like
Okay.
it's your MRI. You need to know where it's coming from. We have no idea, right? Whatever MRI I will drag here, I will get
Yeah.
segmented. But we have much more robust model that can run and get us the results, and that can run on any kind of, well, those are all relatively well looking MRIs, but let me show you. Oh, okay, well, if you have a clinical scan, you know how clinical scans are, the slices are different. So if you run our fast model, you're not getting much out of it. Well, that's it, zero. It didn't see any brain there. But if you run this tissue model that runs for 2 seconds, you get the brain, and at least you can get the volumes, and you know you can get the stuff. Or you can run this. And again, I stress I'm running right on my laptop, and there is no server side. So that's clinical. Let me show you something else. Where's this? Oops. Hmm. Okay, here. So we have pet data, for example, and this is our current state-of-the-art skull stripping model that can run in the browser and generally very fast. And it is omni-model. The same model runs on any modalities. We were hopeful that it would run even on animal data, but it doesn't do that well on animal data. Like, I don't know, let's take T2. So if you need skull stripping, um, this
Yeah, it's pretty cool.
and a good we got good words about usage for CT data. And I'm just grabbing a random file from the files used in, and we can see there's some neck here, right? But it's a CT data, and MindGrab performs quite well across modalities. We can also, well, say the same model. This is T2, not T1 image. And the same model here can give you subcortical and gray and white matter. But I think, okay, that's enough for demonstration. We will come back to it with, again, brainchop.org, the demo that I showed you. Slightly different, slightly better models, more robust, but they will be tomorrow on brainchop.org.
So
But
as somebody will ask here, do you have a defacing model? A model
uh,
that removes the face from like MRIs and CTs. It's
uh,
not that complicated, but we could.
it is easy to make for the following reason. We don't have it, but it's easy to make because for any MRI, any CT, if we know where the brain is and we know where the brain is by running this, and then, well, like this one is already defaced, but we can deface easily on the fly
Yeah,
right here.
it might be a cool application because there are lots of needs for that right now for all kinds of.
Yeah. Defacing is easy, and also QA, visual QA would be right there right now. You defaced and you looked at it. Okay, click on that or save. Oh, let me show you. Let me show you something. So let's go. The important, if I assume an interdisciplinary community that I'm talking to, when you work with different people with different backgrounds. I'm hoping for that neck artifact here. Uh, say the person, yeah, okay, perfect. So there is that problem, right? It gets a lot of neck. One option is to take a screenshot to send it to developer or to send it to the person whose file is that, who gave you the file and ask you to process that. But we have much better option. So what you do, you press here, save scene. Now it's preparing it. And you have, okay, here, you have this file now. What is it? 10 megabytes. You can email it to anyone, assuming email is private, email can be encrypted. You can email it. They receive it in the email. They open, well, brainchop.org. They drag and drop, and they see exactly what you saw, exactly where you chose them to look with your location. And That's a communication tool with radiologists who do labeling, with other domain specialists who are not engineers, who don't want to fire, I don't know, Freeview, AFNI, or whatever tool that you're using to view the images, right? So that also very convenient to collaborate, to work with other people. I think, yeah, I'm ready to move on from here. So, brainchop.org has this tiny, wonderful models, but it's a browser, and a lot of work is non-interactive. Or a lot of us, wait. A lot of us also think that terminal is more interactive and more powerful. So now back to the ML engineers or developers or people who write their scripts. Can we use those fast models as in your scripts rather than only in browser? And we made Brainchop CLI for that to confront the following situation. This is Fast Surfer, a deep learning version of Free Surfer, which is good and everything. I mean, it works beautifully and it is fast and everything. But if you open the documentation, just the installation page of Fast Surfer requires a lot of knowledge. We want it to be just this, and we made it to be just this. Pip install Brainchop. So let's do it. I will create some repo. Say this, and I will activate this repository. You don't need to use UV, it's just faster for the demonstrations. And I guess I can just do this for the video. So I've installed Brainchop, right? And let me... I have this file. let's look at it quickly. Yes, it's the same image that we are looking in the browser, good for the demo. And so I have Brainchop. Um, Brainchop has help, how to use it, etc., etc. So let's run a model, default model on Brainchop. And it tells you which model, you run the segmentation, and you got the segmentation result right there. Just demonstration. The same models that we have in the browser, or at least three of them, or well, four of them. MineGrub is also there. Are available
Oh,
for scripting. You can use Brainchop. Again, it's fully local installation. It's no headache, no like configuring environments. You can pip install anywhere where you want, and you will have sometimes even uh, it may be faster, but we worked hard with web GPU for this to be at the same speed. Well, now it's compiling. Oh no.
yeah, don't worry about it.
Yeah.
It's
Let's.
not a software demo unless it fails once, then it shows it's real.
Oh no, it shouldn't have failed. I mean,
Yeah, no, but
okay. Let me. That's good. Let me copy that.
it just shows that it's real. You're not showing a recording.
It-
Yeah,
okay. But this is the command line demo, and let me escape the shame back into the slides. Well, we'll fix it. We'll fix it. So runs in browser. We also have a Docker version. So if you need to use Brainchop in terminal or in the cloud in your scripts or on your local cluster, it's pip install Brainchop. And if you like, it's especially useful if you have a GPU of any sort, and multi-core CPU. You have to have besides pip install Brainchop, you have to have OpenCL installation for it to be super efficient. But otherwise, if you have any kind of GPU, and I will show you examples of performance. Another thing we noticed that people started using our models from Brainchop CLI in their tools by instead of calling Brainchop, pip install Brainchop and calling it, and just pointing into the code that we didn't think we are not allowed to change anymore. So we quickly made API available. So if you're building something, this is for the builders, kind of against my motivation. But if you're building something, we have API. Just pip install Brainchop and use it via API in your scripts. So uh, the demo, I will show you more, a little more demos in this. But am I allowed to go technical, a little technical, like how it was
yeah,
built?
we can take another 5-10 minutes here and then before we close. Yeah, I
Oh, okay.
will
Maybe,
go.
maybe, maybe, maybe I can go quickly. Okay, so the training is done on synthetic data, and we utilize MongoDB for throughput. It's a key value pair, not that important. And we use Synsegs data generator, which basically only uses the labels. No real brain is used in training for the robust models. For the tissue model, the model with the lightning, the ZAP model, it's fully trained on HCP data, HCP young adult data set. But synthetic deformations, sampling, basically this approach is called domain randomization. We train on noise. We train the model on noise. And this approach was developed and kind of made popular by Eugenio Iglesias from MGH. But also, say, SynStrip uses the same approach for training for skull stripping. We're kind of on par with SynStrip in quality at 5% of the parameter, and I will show you the results of the speed. Let's keep that very technical detail on how the training works. So the most popular model for this kind of tasks, and that's what SynStrip, SynSeg, and any SynStar models are using, and anyone who's doing segmentation is using, is UNet. And UNet is, here it's architecture. It's a fantastic model. If you trust wisdom of the crowd, lots of people are building on it, just tiny modifications and a new paper and use. But there's a problem with models like that. And this model will never be able to work in the browser. Well, unless it gives you all available power, memory and everything. Eventually, probably. But by the time, I hope we will be also far away. So the problem is parameters and memory usage, right? So this small unit, you have down converting or telescoping layers that down sample the input. Input is a 3D brain, and then they upsample it back to the 3D brain, but they have those skip connections to preserve high frequency information. And because of that, it's 23 million parameters. So skip connections need memory when you run the model. Even though you already computed this branch, you will never go back in computation. You computed it. Everything that you've computed, all of the activations must stay in memory because they will be added at the end. And so memory footprint is huge. This is like we used to train on subcubes years ago. In 2017, this model that we're using was, we developed it. We don't do it anymore. So UNet can be multimodal, can be unimodal, etc. So, but full volume training is much better. For UNet, it requires 80 GB. We can train on 11 GB cards, 2080s, and simple. So with MeshNet, we just dropped all of the skip connections. It's a simple VGG style network, but with dilations. The key in our schedule is dilation. We used to use this dilation. Again, this is 2017 when we introduced it. Now a different dilation schedule is used. And a model with the same performance as UNet with 23 million parameters has only 72,000 parameters. So small parameters, small memory footprint, and our 5-channel MeshNet is very, very tiny compared to UNet. Now, back to other applications, the applications where Brainchop and those models can be applied. So here's our mind graph that we're proud of. This model is robust. I recommend using it on any modality. The failures with CT scans are to demonstrate, but if you run on CT scans, you will see how good it is. It works on any device, as I said, that has any kind of GPU. You don't have to have NVIDIA. Almost all laptops have a GPU, for speed. And if you compare a dice score on Flare, on CT, T2, T1, I'm showing you just 4 examples here to impress you, where we statistically significantly better than everything. SynStrip is state of the art. Robex and BET are out of date right now with SynStrip and MindGrab. But notice how close are the numbers. So my claim is that MindGrab performs as good as SynStrip. Those are specifically significantly good, but as good would be enough. And look here, it is anywhere from 14 to 42 times faster, and it uses anywhere from 33 to 40 times less memory, and the results on all of the modalities look about like that. I have more diving into nitty-gritty details with statistical significance or not significance, or like being worse, being better. But if you look at it, we're within 1 or 2 dice points from SynStrip. So practically anywhere SynStrip is used, MindGrab can be used. And again, across all like different modalities, different qualities of the data set, we FreeSurfer now has MRI underscore synstrip as a standard tool. So if you're using FreeSurfer, you can just try that around that, or you can do pip install Brainchop and use MindGrab instead. And this is what we're comparing: the Brainchop tool with MindGrab as the model and MRI synstrip. And again, those are our improvements in time. What's the smallest one here? 9.4, and the largest is 39-ish, so around 40 times faster on this specific Apple laptop I'm giving my presentation from. And memory footprint is also much lower than Synstrip. The way it looks like, I mean, the failures here for BET and others. So there are some differences, like there is a slice missing in this specific blurry image, and ground truth goes over the missing slice, but all other models are unable to, are missing this. They are doing something like that at MRA, but this gives you an idea of how it works. How it fails also, the ground truth is blue on those images, like a few failures that it gives. And those failures are not important as I think. They're not significant when you're extracting brain. This is just a little bit. And as you see, often MindGrab's orange mask is smaller than the blue mask or ground truth. And if you look at precision recall curve, comparison with Synstrip, you can see that MindGrab has higher precision. So it is risk averse in a sense. Anything that it will predict will definitely be in the brain and doesn't want to go too much outside of the brain. But we have a parameter border. You can add border. You can, like, if you really need to predict more and extract. Another thing, it's a recent paper. We trained models that we're using in Brainchop to do tumor segmentation, not tumor, stroke lesion segmentation. And those models can run in the browser, and some of the models that we compare with are 1,000 times larger in their parameters, and they're either worse or at the same performance. If you think about it's the further to the right you are on this plot, the smaller number of parameters you have, and the higher on the plot, the better accuracy the model demonstrates. So our models are on Pareto front for that. And another demonstration, back to the demonstration, we have the side brain to print. So if you have an MRI, preferably your MRI, and you want to print it, then there is an elaborate guide again online how to convert your MRI by running FreeSurfer and etc. etc. But if all you want is just to get a file that you can upload to lots of available 3D printing websites that will ship back the model to you, then go to Brain to Print, drag and drop. Again, I don't want, it's the same file. Drag and drop your MRI, run, I don't know, one of our Brainchop models here, and then go to create mesh. Because we're doing it online, you can make it hollow so that not a lot of material is used, so you're saving material. And it is running. It'll take time. And you have a 3D mesh now. What does that mean? You're saving the mesh. We will go with this. Brainchop. You got the result. that you can, as some people do, and you can upload to Blender 3D or any 3D software. You have the surface, but what's important is that if you save it as an STL file, you go to any service that 3D prints on demand, upload it, they print it for you, they ship it back to you, and you have the tool. We know this service is being used by people. It's a nice souvenir for participants in a study. Give them their 3D printed brain as a token of appreciation.
Okay, we need to wrap in about 5 minutes. So if you get to the end.
Yeah, I don't have 5 minutes, that's fine.
I
So
I
here's
know
somebody.
that I know that one person in a private chat message said that he's already running your models, testing them here. So
Thank you. Yes, give us a star on GitHub. Seriously. So somebody, I don't know, but somebody on Twitter, on X, posted this video recently where I guess I think they're academics, and well, I mean, I'm sure they're academics. They must have participated in a study. Him and his girlfriend, and here are their brains. And so he made this video and put it on Twitter. Just yeah, so you can, well, the other uses of the tool, and then I will skip that. WebGL, just for you, in 2 minutes. What we're using TinyGrad in the CLI tool and in creation of WebGL models. And interestingly, that we're probably the only debuggers and the person who develops web GPU in TinyGrad, web GPU export or backend. We know him and we work with him, and so we're pushing that in TinyGrad, and it becomes very easy in Brainchop. We just export the model to web GPU shader and save tensors, and that's what we're using on Brainchop. Web GPU is fast, but you should be worried because it's just two people working on that, right? Like my team, Mike Dunn from my team, and a person in Hungary. So it's not yet a finalized standard. That's kind of a problem with it, but it will become a finalized standard soon. Brainchop.org tries web GPU if it's there, and if it fails for various reasons, Firefox claims it supports WebGPU, but it doesn't. It falls back to WebGL version 2 and tries a few things, runs it differently to succeed. The WebGL version will run on your phone, the small model with a zap with the lightning sign. So that's my technical side of it. And that's it. The future, we want to make it interactive. We want to make it work in the following way. I want to be able to run a model, and we already have, and I want to be able uh, to say, claim that this is wrong. Manually claiming this, manually doing that is tedious because I only marked one slice. But I want the model to take this into account and correct the entire output based on user preferences. Like, oh, this was wrong, and it will rerun in half a second with a new result that takes my correction into account. So instead of putting control points on making corrections everywhere else, I want to be able to quickly brush stroke correct the model if it made a mistake, get my new result, QA it, and export it, save it, and I'm done. So that's where we are going with it. And I already see somebody give us a star. Thank you. That's all. Should I stop sharing?
yeah,
If you have, this is for the YouTube channel. Thank you for watching. Yeah, if we have any questions right now, I'm ready.
I'm
And
going to stop the recording here. So if anybody has any questions, but yeah, I know that.